Okay, so if the last few videos, if you watch them, they're pretty straightforward. This one's not so much, so you want to be careful on this one. For objects that are being moved in a circle that is vertical, so this is up. In order to move at uniform circular motion, the centripetal force isn't always the same, because gravity affects things. Remember, centripetal force is the net force. Well, here, sometimes gravity, and I think we've looked at these in class, sometimes gravity is working with the object that's being swung around, pulling it towards the center. Other times it's doing the exact opposite. And other times it is a non-factor. Let's look at the non-factor. So probably if you get one thing out of this, if you're swinging something on a string or a stick, or you're swinging something around in a circle, generally the tension, right, in this case we're swinging an object on a string, and there's tension pulling it that way. When the object in question is either in this position or this position, 90 degrees left or right, horizontal from the center, in those cases, gravity is no component of gravity is working inward towards the center. So we can say at that moment, if we know the tension, that is the required centripetal force. Keep that in mind, because say for example here, at this location, gravity is working with you, and so the tension doesn't need to be nearly as much to produce that same centripetal force. So the tension will be zero, or will not be zero, it will be less. It could be zero even, depending. If you needed a centripetal acceleration that was exactly g, then the tension would be zero, because you would not need any tension. Gravity would be able to do that exactly. So at the top, your net force is equal to, and therefore your centripetal force, is equal to the combination of mg and tension. Both negative at that point, so maybe we do that, but they're going to combine. Whereas, down here at the bottom, here, gravity is working against the centripetal force. In other words, it's diametrically opposed. It's straight down. We need the centripetal force to keep this uniform circular motion. Needs to be the same size it was here. So that means your tension has got to be large, because the net force at this location, which is the centripetal force, has got to be tension minus the weight. So the key here is wherever, if you can have a problem, if you know what's the tension or whatever the normal force is at, not normal force, whatever the centripetal force is at this point is what that centripetal force will need to be the entire time if we're going to keep the velocity the same, uniform circular motion. Now, another possibility here is normal force. In other words, what about a car or something going over a circular hill? At this point, here's your car going over the hill. Normal force actually pushes up and weight down. So in order to move across that curved surface, the net force, which is the centripetal force, is going to be normal force minus the weight. And you need weight to be larger, because otherwise you're going to come unglued. So the point at which you will lose, if you come over this hill, and if you're going too fast, in other words, if you require a centripetal acceleration that's too much, you could fly off the hill, lose contact with it. When will that happen? When your centripetal acceleration is required is greater than g. The best you can hope for here is g, because gravity's no one's got a rope attached to you pulling you downward. The only thing that can pull you towards the center of the circle is g. So if you're moving at a speed that requires a v squared, right, over r, if you're moving at a speed or going over a hill that's curved enough that you require a centripetal acceleration of 11, it is not going to happen. You're going to come out of contact with the ground. So keep that in mind. think. That's all you need to know for this.